All right, good morning. Welcome to the first tech session here on stage number 3. And we're here today to talk about mission critical push to talk and interoperability with LMR, or land mobile radio. So let me start off by introducing myself. My name is Mark Fetchy. I am Vice President of Sales for Motorola's Critical Infrastructure and Enterprise Group. And our focus is mainly on electric utilities, oil and gas, other critical infrastructure companies, as well as some Fortune 500 companies. You may know Motorola Solutions, long time in the land mobile radio business, but Motorola has expanded beyond that, so come see us at our booth afterwards if you want to hear more about that. But I know this is not supposed to be a sales pitch. So why I am a former engineer, the person who's going to be doing most of the talk today has a lot more technical expertise than I do, and this is Madhu Pai. Madhu is a business, technology, and cybersecurity leader in broadband communications. He has had various leadership roles in Motorola Solutions across development, project management, system architecture, cybersecurity, and product management. And he has been the chief architect for Motorola's broadband MCX, or mission critical push to talk, mission critical push to video, and LMR interoperability solutions. He is what we call an MSI, Motorola Solutions Incorporated Distinguished Inventor, and currently holds 19 U.S. patents. In his current role, he's the system owner for what we call our unified communications portfolio, which is where our MCPTT and LMR interoperability products lie. So Madhu will be doing all the technical talk, but I'm going to kick it off today to talk about, in general, what we're going to talk about, and then try not to break my iPad. What is the need that we see today in utilities for mission critical push to talk and LMR interoperability? So I'll talk a little bit about the drivers, and then Madhu will go into the technology evolution, how you would integrate an MCPT X solution with an LMR solution, and talk a lot about standards, because all this MCPTT that we talk about is a standards-based product, it should be a standards-based product based on the 3 GPP standards. So he'll talk about that as well as interoperability and security. So why do utilities need an LMR MCPTT interoperability? Well, as most of your utilities, you probably know, you've spent a large investment over time in a very robust LMR network. And while that's great, the LMR networks of today, they don't do a whole lot. They do push to talk. Push to talk, release to listen, great for instant group communication. But as a utility evolves, that basic LMR functionality is not all what's needed. A field worker today needs more than just voice communications. And today's LMR networks don't offer that. Yes, they can do some data. I've put, in my engineering days, I put very limited data applications over an LMR network, but in a 12.5 kilohertz channel, you can't get a lot of data. So a GPS update here and there, some type of data alerting, you can do that. But today's field force workers need more. They need more data. They need more information for when they're doing their job. And also, traditional LMR networks aren't interoperable amongst themselves. So your utility may sit right next to another utility service territory, and you can't talk to one another. So how do we solve this need for more information in the field beyond just voice, and the ability to interoperate together? Also, traditional LMR networks, very high power, rugged devices, expensive devices, as you probably know, and a lot of utilities were reluctant to put that into the hands of an office worker or of an engineer in some cases, because it was a rugged field device. So how do people who are working on the line, working in the substation, working out on the gas pipeline, how do they talk to, in a very quick and efficient way, talk to people who might be carrying something like this, a cell phone, or some other non-rugged device? So the overall vision for LMR and MCPTT interoperability is to put the right device in the hands of the right person. and being able to communicate on any device over any network and being able to create instant ad hoc communications between people as needed. So that's a little bit what we're going to talk about today, the need for that. But in general, as I said, your utilities have spent a lot of time, a lot of effort, a lot of money on building very robust LMR networks. And any type of MCPTT network and interoperability needs to have a lot of those same, not a lot, it needs to continue with parity on those same features. So when we think about LMR, LTE interoperability, we put it into 3 pillars, and they're kind of, unfortunately, not grouped too well here, but we think about broadband-only features. I mentioned on a traditional LMR network, very low data speeds. You're not going to get, you can't put video across it. You can't do real-time GPS updates where, you know, I can pick up this device today and watch my kid speeding down the highway and then yell at him later because he was going too fast. You can't do that over a traditional LMR network. You need a broadband communication. So there's purely broadband-only features, which are kind of the first pillar. The second pillar is what we would call LMR parity, the ability to have one-to-one communications, the ability to have one-to-many communications, emergency calls when somebody pushes a red button on top of their radio, or to be able to notify someone in the control room immediately that they are in distress. So having the LMR parity features as well. And then finally, LMR interoperability, being able to do those, to have a call, an emergency call on your LMR system, bridge across to an MCPTT system, and still have the same level of priority and preemption that you have in your LMR system. And then direct mode. One of the great things about LMR is you can go off network. Most of your field radios probably have a talk around mode or something like that, where you don't, if for whatever reason the network goes down from a hurricane or an ice storm and you've lost your tower site, you still have the ability to communicate with people in your general area using direct mode. So that's another one of those LMR parity features that you need to take into account when you're thinking about an MCPTT solution. So that's kind of setting the stage for Madhu, our expert, coming up and talk about what we call solving for safer utilities, but being able to be unified. Apparently, we've got a problem with the microphone. Okay, we're good. Being able to be unified, instant, secure, and reliable communication. So Madhu, come on up. Are you just going to be down there?
Yes.
I'll turn that over to you.
Morning, folks. Can you hear me okay? Yeah. I'll do this on the floor so it'll be much more intimate with all of you. Come on and sit, please sit. There's going to be questions for the audience and there's some homework later. I'm going to share some QR codes with you to send me stuff, so I'm just kidding. Please sit, come. Thank you, Mark. So Mark gave us the intro on the 3 pillars of what an MCX solution. The MCX here is X is PTT or video or data. That's the way the 3GPP mission critical standards have defined these solutions. The MCX pillars are broadband native. What features work best on broadband? Video, multimedia attachments, situational awareness. What are the features that are required for LMR parity, and then LMR interoperability. That solution can be deployed in 3 different modes of delivery, and that's what we'll delve into on this slide. On the x-axis, we have an increasing amount of network and device integration, and on the y-axis, we have a corresponding increase in the use cases that you can offer with the solution, going from basic group comms all the way to mission critical. Now, the MCX over the top tier, this is where we deploy the solution in an over the top fashion with minimal network and device integration. And again, this doesn't mean there's none. There are capabilities that we will deploy network integration with. We'll do, for example, access class barring. We'll do shorter DRX cycles on the network, so on and so forth, and make the PTT call setup experience better. As we head into the MCX QoS realm, this is where we integrate with the network on 3GPP standards-based interfaces, with the RAN, with the PCRF, over 3GPP RX, for example. And this is where we enter into a contract with the network. At the beginning of every call, we establish a contract that says, my voice is going to get to each one of you over a guaranteed bitrate voice pipe. That's the first time we start doing this in the MCX QoS realm. The MCX LMR parity realm is where we get even better in our network integration. Just as I'm speaking here today, when I say the word MCX, all of you hear me at the same time over a broadcast medium. The network supports broadcast capability. On 4G, that technology is called eMBMS. 5G, they made the acronym more spelling friendly, it's 5G MBS. So the MCX solution takes advantage of broadcast capabilities in the network in this. Now, obviously to do those, the device integration also increases. We integrate with different vendors for different types of middleware in the broadcast category. The MCX QoS is fairly standard now. All standard chipsets support the MCX QoS enablement. How many of us familiar with LTE, 5G, bearers, and so on and so forth? Show of hands, please. Awesome, some, few, very good, thank you. I'll do a quick 30-second run through of what this means. So later we can see the value of how this technology brings mission critical service delivery to each one of us in the room. I'm trying to find the mouse click. Yeah, it's too faint, yeah. That's okay, I'll try to do it. So there's a concept of a bearer in the network. Now we can think of the bearer as a pipe. The pipe may have certain capabilities. The pipe may be a non-guaranteed bitrate pipe, which doesn't guarantee the bitrate you need, but it can be prioritized to carry signaling data. So for example, in a congested network, if you want to carry the request to set up a call through the congested network into the infrastructure and to the PTT server, you would use a higher priority, non-guaranteed bitrate signaling pipe. So that's called an NGBR or a non-GBR pipe. Next, we talk about guaranteed bitrate pipes. Voice, for example, a voice call with say AMR wideband with encryption would take roughly, for ease of calculation, about 40 kbps, 40 kilobits per second. We need this to be a guaranteed bitrate pipe through the network when I'm talking. Otherwise, you'd hear choppy audio, you would hear lost audio, and so on and so forth. Right? So that's the unicast guaranteed bitrate pipe. What does unicast GBR mean? When the server sets up a push-to-talk call, it goes to the network, it sets up a guaranteed bitrate pipe for each one of you in the room. So when I'm talking, my voice goes over a guaranteed bitrate 40 kbps pipe to each one of your devices so that you can then render it crystal clear audio. Sounds like a lot of work, but this is done in like 150 milliseconds at call setup for all of the devices in the network. So that's the magic below the hood. As we grow the network, as we grow the number of users in the cell and we want to take advantage of broadcast guaranteed bitrate pipes, that's the one pipe that all of your devices can listen to at the same time. That concept is called a TMGI, or a temporary group identifier, right there at the bottom. This is where the eMBMS and MBS enable the network, enable the MCPTT solution to create these broadcast pipes in the network and then send voice out over those broadcast pipes. Right? With that background, the MCX over-the-top solutions, they deal with the non-guaranteed bitrate pipes. Right? Again, this has a very important role to play. The MCX over-the-top solutions are ubiquitous. Any network, any device, the solution will work. Right? Now, when there's congestion, things get bad, and therefore you need to go into the higher segments. In the MCX over-the-top segment, from a technology perspective, we can make things better. So we can do class barring as an example. Folks on the RAN who are familiar with ACB, it's a little asymmetric. In a congested cell, if you're using access class barring, the lower priority users will not initiate calls, but inbound calls will still terminate on lower priority users. So the higher priority users are kind of at a disadvantage. It's a little skewed. It's not perfect. ACV is not perfect, right, for various reasons. Similarly, you see there are lots of offers out there with a higher priority non-GBR bearer. What does that mean? So the YouTube, the Facebook, your regular applications will be on the default bearer that you get. So for example, on a carrier subscription or on a private LTE subscription, when you latch onto the network, your device gets a default bearer. That will carry all of your regular traffic. You could elevate the MCPTT traffic onto a higher priority non-GBR bearer. So you're giving it a different higher priority pipe to provide service. Those concepts are available with the MCX over-the-top tier, again non-guaranteed bitrate. When there is congestion, the non-guaranteed bitrate bearers will starve. So there is starvation on the NGBR. We then move to the first layer where we start talking about guaranteed bitrate bearers, and that's the MCX QoS layer. Here, the MCPTT solution integrates with the carrier's PCRF or the 5G PCF over a 3GPP standard interface. We can use RX, the RX interface, that's 29.214, or the newer variants on 5G. And we can then go set up these guaranteed bitrate pipes. How many of us have VoLTE running in their networks? Show of hands. Anybody runs IMS VoLTE? Voice over LTE? Okay. So in carrier networks today, IMS VoLTE is available. That is what we use for calling, like the one-to-one calls we make using our cell phones. That's running VoLTE. VoLTE uses GBRs today. So when we deploy this, let's say over a shared network or over an IMS network in which voice over LTE is currently running, if MCPTT is running in the over-the-top layer, IMS VoLTE is already in the QoS enabled layer, you're at a disadvantage from get-go. MCPTT is at a disadvantage. When we move MCPTT up into guaranteed bitrate treatment, that's where we get parity with VoLTE. We can now interleave VoLTE priorities and MCPTT priorities. You could say emergency VoLTE is higher priority than emergency push-to-talk, higher priority than, let's say, broadcast push-to-talk, non-emergency VoLTE, non-emergency push-to-talk, so on and so forth. And this gives us the capability to introduce these different data applications in a way that they can use the network with the right priority. An emergency push-to-talk call could preempt a lower priority non-emergency VoLTE call or a lower priority non-emergency push-to-talk call. This scheme. In this scheme, the MCPTT server is aware of the state of your GBR pipes. Remember, the server is entering into a contract with the network. So at call setup time, the server goes and establishes the contract. If the network is unable to meet the contract due to congestion or whatever other reason, the network is going to give feedback back to the server saying, hey, I lost that pipe to this particular device. Mark's device no longer has the GBR treatment. The server is therefore bearer aware, and it can make the right call control decisions. So Mark will get a busy, or Mark's device will be removed from the call, so on and so forth. Mark's device will not starve. So you won't have the, hey, can you hear me problem. You'll have a very deterministic end user experience once you move into the MCX QoS layer. Right? That's a significant advantage of doing this. LTE as a technology, so let's say you are at the cell center, right? And you need to deliver 40 kbps or ease of computation kbps voice to that device. As you move from the cell center to the cell edge, the number of over-the-air resource blocks to keep that 50 kbps commitment or the contract increases, right? So effectively the guaranteed bitrate throughput in the cell will come down due to mobility reasons or due to congestion reasons. As more applications requiring GBRs come in, more calls come in, you're going to see congestion. That's when the GBR capacity of the cell fills up. Quick show of hands, I'll ask for some volunteers. Please don't tell me names of the vendors that you're using in your network. In your network on a given base station, how many devices can latch onto it? Any volunteers? Okay, I'll take an example base station. I won't name the vendor and I won't get into the channel megahertz and so on and so forth. 5,000 users roughly attached to a base station in an exemplary base station embodiment. Okay. Now, that means 5,000 devices can latch onto a base station, let's say outside this convention center, and they can remain in idle mode, which is the radio resource idle, RRC idle state. They can remain in the RRC idle state. Out of these 5,000 devices, when these devices need to send data or receive data, they need to get into RRC connected state, so they can receive and send data with the network. Now, typically, what percentage of devices that latch onto an eNode B can switch to being simultaneously RRC concurrent, RRC connected state? Any volunteers? So with the 5,000 devices RRC idle eNode B, roughly 1,200 can go to RRC connected. And now, if I need to deliver, let's say, a 50 kbps voice stream to each of those users because they have to get into a push-to-talk call, what is the GBR bandwidth I'm looking for in that cell? About 1,000 times 50 kbps, roughly 50 Mbps, right? How many of us have eNode Bs with 50 Mbps guaranteed bitrate delivery throughout the cell? Right? So you start, as your groups increase in size, as the number of concurrent group calls you need to run increase in the network, you start seeing capacity issues with GBR traffic, and that's when we move into the broadcast mode with eMBMS or the MCX parity layer, right? And we'll get into that a little bit more. There are several other advantages of eMBMS. Now, eMBMS as a technology, two base stations, and as I move from one base station to another, the two base stations are sending data at the same frequency at the same time, so they are time synchronized. Which means at the cell edge, when I'm moving from one cell edge, one cell to the other, there is constructive interference, and I'm actually not losing audio, I'm getting better audio at the cell edge. Unlike the traditional unicast on the devices that we have today in our pockets, as we move from one cell to another, you start stressing the network more at the cell edge to maintain that guaranteed bitrate. But with eMBMS, your cell edge is better. You have constructive interference for mobility. Another key advantage of eMBMS is synchronized audio and video delivery. As an example, we have 10 devices here. If we were doing a push-to-talk call, even with guaranteed bitrate pipes, all of the devices would be rendering audio on the speaker, let's say about 10 or 20 milliseconds apart. So at an incident scene, when you have these 10 devices playing out my voice, and all of them are going off maybe 10, 20, 30, 10, 20, 30 milliseconds apart, it's a very distracting human listening experience at the incident scene. Right? The same voice coming out of 10 different speakers, let's say at home you have a home theater, and voice is coming out or the sound is coming out of 10 different speakers at 10 milliseconds, 20 milliseconds apart. Very, very distracting human experience. eMBMS also solves that problem. For an incident scene deployment or for a dense congested cell, if you have more number of users with devices in that cell, in close proximity, all of their speakers are rendering the voice at the same time. So it's not really surround sound, but it's more a stereo, it's more comparable with a stereo effect. Multiple speakers around you rendering the same voice at the same time. That's another key advantage of eMBMS. We spoke a little bit about RRC idle. Now, eMBMS allows RRC idle devices to also receive voice and play it out on their speakers. They do not have to go to RRC connected. So let's say I'm setting up a 500 member group call in a site. If I were in the over-the-top or in the QoS enabled arena, the PTT server is going to be replicating the voice. So when I say push to talk, the PTT server is going to replicate that push to talk voice packet 500 times to each user. The PTT server is going to the RAN and requesting guaranteed bitrate pipes for each of those 500 users. The RAN is going to page 500 devices. The devices are going to wake up, move to RRC connected, and that's what we loosely call an RRC connected storm at the eNode B. All the devices are trying to get to RRC connected at the same time. Once they go to RRC connected, the PCRF or the PCF is going to establish the bearers all the way through the base station to the device. That's the contract with the network to keep this 40 or 50 kbps voice flowing. And then we let the voice go. Now, in the MCPTT world, we do all this within 350 milliseconds. right? You can do it much better with eMBMS because all the listening devices, the 499 devices that are listening, they can remain in RRC idle. So there is no RRC connected storm. There is no PCRF bearer set up for those 499 devices. Only the talker needs a bearer. And all the listeners are receiving the audio while they are in RRC idle. Right? Now, in terms of the bandwidth, instead of setting up 500 times 50 kbps pipes, I'm setting up one eMBMS channel for 50 kbps that is broadcast, and all of the devices are listening to the same channel. It's very much like your radio network at that point. Right? With video, it's a slam dunk. The bandwidth, if the video that we want to send is, let's say, 5.1 Mbps for HD, and all the devices have to receive that video, or even few of them in that cell, 10 of them in the cell have to receive that video, sending video over eMBMS is a phenomenal bandwidth saving. Right? So some things to consider when you see the MCPTT evolution, the MC video evolution, and how things are going in the network. What are the investments we want to do in the network to make this work? Another key point with this slide is an evolution. At the same time, it's also inclusive. In the solutions that we build, the same group, a group of let's say 500 users, can have multicast or broadcast service delivery. 400 of them can be in eMBMS capable areas. 50 of them may be outside, and they may receive delivery over unicast GBRs. Another 50 of them may be on Wi-Fi, or some of them may be wireline dispatchers, right? So this entire segment can be in the same call at the same time and receive the appropriate mission critical experience based on the network they are in and the capabilities of the network and the device that they are using. So this is not just an evolution, it's also coexistence in your network at the same time with the same application server. So a little bit of pictures on what we spoke about so far. This shows if you have IMS VoLTE in your network, how IMS VoLTE is at an advantage. It can punch through the congestion cloud. The color is perhaps not so great in this rendering, but the green cloud, shouldn't be green for congestion, should probably be red. The green cloud is congestion, IMS VoLTE punches through this. The dotted line is the non-GBR bearer. So the non-GBR bearers get prone to congestion, there is starvation, there is the lossy audio and so on and so forth in this scenario. When the MCX server is enabled with the MCX QoS layer and is talking to the network and setting up this contract, you can now have the guaranteed bitrate pipes set up in the network for PTT calls. The different colors are just for different priorities. You can have higher priority, medium, lower priorities. The standard allows up to 15 different priorities. So if you have different user populations in your network or different groups for different types of services, high priority, medium priority, low priority, you could have this priority of the application go all the way into the network. So there's application priority, network priority, bearer priority that reflects exactly what you want in your operational use case. An emergency call will be the highest emergency priority in the network all through the broadband system to the devices. And when we do interoperability, remember with interoperability this emergency call meaning with emergency priority in LMR. Now both your systems, LMR and broadband, are running the same emergency call with the same highest emergency priority delivery in both networks at the same time. That's the power of network integration. And then of course this is eMBMS. Again, dense groups, multiple concurrent calls to dense groups, capable, enabled by capacity increase with eMBMS. We also spoke about when you use eMBMS, you're actually saving bandwidth, you're returning back to the GBR pool. So applications that need GBR for unicast delivery now can start using back from that GBR pool. Instead of setting up the 550 kbps pipes, I set up one eMBMS pipe in that cell. Other devices or other applications can use GBR at that point. Now a quick look at the standards arena that enables this technology. So we spoke about 3GPP. 3GPP has been defining standards for MCPTT, MC video, MC data over different releases. A little bit of an eye chart here, I apologize for that, but somewhere here are the dates. So you can see they've been working on this for a while, and pre-release 13, there was a different bunch of standards that evolved into what was then MCPTT. So different people around the world on the network side, on the devices side, on the application side, on different infrastructure elements have been contributing in this space. By around release 16, roughly, MCPTT, MC Video, MC Data, and the use of these GBR aspects and the use of multicast delivery aspects are quite well defined in the standard. And there's more stuff that's coming. 5G MBS, 5G broadcast is happening. The railways, which may not be of a lot of interest here, but FRMCS for the railways, that's happening. For LMR interoperability, there is work happening on interworking functions, and we'll talk a little bit about our own LMR interoperability in a bit. And then there's the concept of an MC gateway UE, which also we'll talk about in the context of LMR interop. Now, when you evaluate a solution that is saying we are 3GPP compliant, what does that mean? From a 3GPP standards perspective, the standards bodies have defined 3 layers of standards, if you will. So stage 1 is the value of the solution or the requirements. Thou shall support one-to-one calls, thou shall support group calls, your solution shall support emergency alarms. So that's the feature set or the value of the solution that you provide to your end users. Stage 2 is all about the architecture. So they have said, how should your solution plug and play with other system level components, with the operator's network, with the IMS, etc., over standards-based interfaces. Stage 3, they've also gone down to the level of protocols, bits and bytes, saying between the client application and the server, or between the dispatch and the server, what should be the protocol bits and bytes that you should use. Now that enables, let's say, an MCX system to have a third-party dispatch from a different vendor. Identity management, authentication, authorization, if you would like to offload that to your existing identity management solutions and have an MCX system work with your identity management, that's possible if they follow the standards-based identity management, OIDC protocols, for example. That's possible. So protocol bits and bytes compliance allows you to plug and play different components from different vendors. Let's now switch a little bit to LMR interoperability itself. LMR interoperability comes in at least 3 tiers of solutions. The lowest end of the vanilla tier is the donor radio. Now, just because I call it the lowest end, it's not bad. It's a great solution when you have a need for small number of talk groups. You don't want to spend a lot of money. You don't need to cover statewide or large number of maybe even nationwide systems. This can do some basic features. The way the donor radio works is, how many of us have seen a donor radio device? Few of us, thank you. So the donor radio, for the rest of the audience, is like a back-to-back, let's say you have an LMR device and a broadband device, and there's just them. So it's like strapping a broadband device and an LMR device to each other, and you can allow one talk group to interoperate. One talk group in LMR interoperates with one talk group in broadband using the donor radio bridge, right? So obviously because of this it scales poorly. If you want to do this for tens or hundreds of talk groups, it's going to be quite an exercise. Let's just put it that way. So we start then getting into wireline interoperability. It is fairly common to start deploying console-based interoperability. Now the console is a high priority user in LMR and broadband systems. So a console vendor here typically deploys 2 stacks, one stack for LMR, a different stack for broadband, and the console application then bridges the 2 worlds. It scales much better than the donor radio. It's in software now versus the 2 physical donor devices that you need to deploy for every talk group. However, there are some priority skew problems. As you know, the console is the highest priority user in the LMR system. So when any broadband user talks, they get console priority in LMR, and vice versa. So think of LMR cadet, broadband officer. I'm picking a public safety example, but I'm sure you can have different hierarchies, right? You can make them up as well. And vice versa, LMR cadet, broadband officer, and so on and so forth. The priority gets skewed. A lower priority user in broadband comes in with console priority in LMR. So that's the problem with a console solution. Excuse me. Which is where we then get into the wireline interoperability with very rich feature set. These are the high-tier voice and data interoperability systems. These support beyond the traditional group calls, you can do one-to-one calls. Your identities flow end-to-end. So if you use a console or if you use a donor radio, when an LMR user, when Mark talks, I don't see Mark talking, I see the donor's identity as the talker or the console as the talker. With wireline interoperability, now I'll see Mark is talking. The LMR dispatcher, when they see a red dot on the map, they can see the identity of that red dot. Is that an LMR device or is that a broadband device? What is that particular device? They can see all of that end-to-end. You can have seamless priority and preemption across the two systems. All of that is possible with the wireline interop. Excuse me. Thank you. I love talking. Excuse me. With the wireline interop, we can now also offer data interoperability. So you can make location interoperable. An LMR device's location can be seen on a broadband console. Broadband location can be seen on an LMR console. You can have interoperable messaging. Messages, operational status, present status can be exchanged between LMR and broadband. You can create a very rich API ecosystem. So let's say there's a workflow application. The workflow application only needs to say, I want to send messages to this group. In the group, you can have broadband participants, you can have LMR participants. The workflow application is agnostic to it. It only sends a message to the group. And at the back end, the API ecosystem goes and talks to the two different networks and sends messages to both the appropriate places. These kind of wireline integrations, we've deployed them nationwide, large systems, thousands of interoperable talk groups, hundreds of thousands of users as well. We can deploy them in a very highly scalable, redundant, even including geo redundancy. We can go deploy that. We'll do another about 5 minutes on security and then we'll jump into Q&A. How many of us familiar with the security on how the internet world works? Okay. So one of the cool things that came with 3GPP was Mikey-Saki identity-based encryption. So today when you bring up a browser, and let's say you have to connect to your bank, the browser has to encrypt data to send to the bank. Right. The internet world works, for example, with transport layer security at a very high level. If the browser has to encrypt data to send to the bank, it needs to have some form of key exchange. It needs to know the public key of the bank, and similarly the bank needs to know the public key of the browser, so that they can then exchange data with encryption in a way that nobody in the middle can intercept that data and see the data in the middle. So when you open up your browser, there's a green icon that shows up with a padlock. There's a lot of technology going on below the hood to make that thing green and to put a padlock there. Fundamentally, there has to be key exchange. Now in the MCPDT world, let's say I want to make a one-to-one call to Mark or one-to-one call to any of you. I want to avoid the key exchange problem. I don't have a way to contact Mark's device and get Mark's keys. Yet I want end-to-end encryption. So before Mikey-Saki, the way this worked was, I knew the server's key, I would encrypt data up to the server, and then the server would encrypt data to Mark's device. Right? So it's not end-to-end encryption anymore. To support end-to-end encryption, Mikey-Saki IBE brought out a unique novel mechanism. All I need to know is Mark's public identity. So let's say I want to call Mark at MotorolaSolutions.com. I can create a Mikey-Saki encrypted payload just with knowledge of Mark's public identity. And nobody else in this room can decrypt it, including the MCX server, except Mark's device. That is the value Mikey-Saki IBE brings to the table. So when you look at private calls, the private calls are truly end-to-end encrypted. Nothing in the infrastructure, including the MCX server, can decrypt it. So 3GPP introduced this concept in 33.180. That's their standard for MCX security. And this is something that the 3GPP based solution should be compliant to. These solutions include a KMS, that is 3GPP 33.180 compliant. And that's how we accomplish Mikey-Saki end-to-end encryption. Now, this is Madhu's view of the world. We'll talk a little bit about security, compliance, and privacy. Now, different companies may draw this circle differently. So, a security company may draw the circle with compliance and privacy inside the security bubble. A compliance company may draw both security and privacy inside the compliance bubble, and so on and so forth. Each of these bubbles are small economies in themselves. Many companies working in each of these small bubbles. Now, when you look at a solution that is giving you interoperability, is giving you mission critical communications over broadband, for example, the 3GPP standards, we spoke about Mikey-Saki IBE. The standards tell you thou shall use Mikey-Saki IBE for key exchange and for encryption and so on and so forth. But how do you store, how does Mark's device store Mark's Mikey-Saki crypto material securely? That's outside the standard. Right? So how do you evaluate your vendors when they come to you with MCX solutions, and how do you go evaluate them for security, for privacy, for compliance? This world has changed significantly over the last few years. Right? So in the security realm, it's all about ensuring confidentiality, integrity, and availability of your solution, of your data, of your network. Different companies adopt different frameworks. I know Motorola has adopted the NIST 853 framework. It's a very common global standard, sourced out of the US and used globally in many different information security regimes. NIST talks about various items, various tenets: identify, detect, protect, recover, respond, and govern. There are frameworks where companies would do risk management, would do application security. They would have a NOC that's monitoring the system. They would have a SOC for security events, for incident response, so on and so forth. All of these can also be audited. There are compliance regimes for it. There are standards such as ISO 27001, 17, 18, data privacy extensions 27701. Companies can prove they are compliant to all of these security paradigms and tenets and the frameworks that they've chosen by getting certified by third-party vendors to these compliance regimes. So when you evaluate MCX solutions, it's also important to evaluate them from a security, a compliance, and a privacy perspective. Privacy is all about user data, users' rights to that data. How is that data stored, processed, retained, shared, if any, so on and so forth. And the US has been traditionally a little, let's just say, slow to adopt privacy regimes. Europe has been a little more active in the privacy area, but we're now seeing a lot of laws, especially statewide in the US. Different states are enacting different privacy laws to protect customer data. So again, from a privacy perspective, there are different certifications that you can go get. It's also important to understand in a mission critical system, you're looking at devices, PII, IP addresses. You can trace a user to their location. Right? For example, let's say 9 a.m. in the morning every day, receive PTT calls from a certain location. It's quite indicative of where I might be tomorrow or otherwise during my normal routine, right? Even if this data were aggregated, you could still figure out, oh, in this system, there are so many users at this particular geolocation. Now, what if you were using a third-party cloud service to send geofence updates? Even if it was aggregated and anonymous, the cloud service would still know this network has so many users at these particular locations, right? Now, what happens to user data at that point? If that data gets compromised in the cloud service, Who's responsible? How do you ensure the cloud service people are following the right SLAs and the right security controls that protect you and your users' information? All of that comes with privacy compliance, right? There are data privacy assessments. You can ask your vendors, what data are you getting from my devices? How are you storing it securely? Are you sharing it with somebody? So on and so forth. So something to consider. In the past, all of these, the triad of security, compliance, and privacy was more of a screening activity. You would build systems, and then you would go through some checklists and say, do I meet ABC controls, right? Just like quality maybe 20 or 30 years ago, it went through the same maturation curve. It was a screening activity, then people figured out, oh, this is not really worth screening. You have to build it foundationally in the product to pass that screening, right? And then eventually we started saying, oh, this is part of our minimum viable product definition. If there were a quality break, it was a stop ship. Similarly today, if there's a security break, it's a stop ship. If there is a security vulnerability in the product that's of critical risk, you would stop ship. So you would want an MCX solution that can display this level of compliance across the board, across the technology spectrum, across interoperability, across standards compliance, across compliance with security, privacy, and the compliance to ISO and other standards. Yeah, something to consider in your evaluation of solutions. With that, hand it back off to Mark. Thank you.
So are there any questions? I know. We'll move away from the speaker. Anybody have any questions? No questions from me, but I do have one because I just want to make sure I'm clear on something. I probably should have reviewed the material a little better before we got up here. But when you talk about over the top, well, I set my device down over there. Over the top, I could go into the App Store and I could look up a PT provider. I could download an app, and it makes critical push-to-talk app. But because I'm just using an app over the Verizon network, that would be that over-the-top section. Is that right? And then I'm just trying to wrap my. Go ahead.
Great question. So the over-the-top segment doesn't mean the ubiquitous app download from the App Store. It's not limited to that. The over-the-top segment, you could take the same device. So let's say we deploy the solution with network integration on a particular device. That device can get the app from the App Store. So getting the app from the App Store is possible across that entire spectrum. Right? Similarly, getting that device to work, let's say, on a dual SIM device, one SIM having network integration, another SIM not having the network integration, roaming to a different provider that doesn't have the network integration is still possible. So when you're in your home network, you will have the benefits of network integration. When you roam, you will work over the top. So the over-the-top versus the network integration is the capability of what is delivered to you with your SIM on your device in your network versus what you do not get working as an over-the-top solution on any network on any device. Does that help?
So it's more than just the application saying it's MCPTT capable. It has to do with how that application is integrated or not integrated into the network. Okay. Thank you.
Any other questions?
Thank you. This is good. So Motorola has an MCX offering. Is that today? And then I guess the follow-up question is, how do you guys see that integrating with like your Critical Connect offering? And do you see it coming in that way or via ISSI type connections between the LMR that exist?
Let me switch to a backup slide. Thank you for the question. So this is not supposed to be a sales pitch, so that's why we didn't include these in the initial slides, right? So, so yes, we do have MCX compliance across the board. We've been pioneers in this space. We have significant technology advancement partners also on the network side, on the device side. We've led the market in this space as well. Now, the broadband mission critical comms portfolio is a separate offering. We call it Wave PTX. We also have Critical Connect, which is for LMR interoperability. Our customers could procure both as separate services as well. And we also have different Wave PTX on-prem offers where we have Wave PTX and Critical Connect instances deployed for specific customers, which give you broadband with LMR interoperability. So there's different tiers. It's a highly tiered offering with exceptional value. We pride ourselves making it best in class, both on the broadband side as well as LMR interoperability side.
Yes, yeah, it can work on other LMR systems. Critical Connect is our IWF at a high level, right, Madhu? Maybe I'm oversimplifying things. I'm putting on my salesperson hat here. But the Critical Connect that we offer is basically, I view it as like cloud-based ISSI, for lack of a better word. So the ability to connect broadband solutions, connect other applications, other networks together through a cloud-based connection, interoperable ISSI type connection. And Wave, where is it up there? It's under applications, I'm guessing. Under broadband is part of that. So the Wave PTX server can be connected to our Critical Connect cloud, which then gives it access to any other network or any other application that's connected to that cloud.
That system, I see Verizon and FirstNet there, so that system is already working in there?
Yes, yeah, our Critical Connect cloud does have connections to Verizon, AT&T, and AT&T / FirstNet. I don't know if it has T-Mobile yet or not. I can't remember.
It does, but I mean, I don't know if it's a recorded conversation. We can't talk about customers so much. But yeah. So we do offer standards-based interoperability with third-party networks out of Critical Connect. That's over ISSI. And we also offer native integration for best-in-class feature set with our own systems, as well as standards-based interoperability with our own systems. It's all available in Critical Connect. And please join us at the booth, and we can talk to you more about it then. Anything else, folks?
Thank you very much for your time.
Stay back for the quiz. Thank you. Thank you all. It's been a pleasure meeting you. Thank you, Mark.